Welcome back to Daily Dose of Space. Today, we're diving into one of the most fascinating, terrifying, and misunderstood objects in the entire universe: black holes. You've probably heard the usual line, gravity so strong that not even light can escape. But that's just the surface. What black holes actually are, how they form, what happens inside them, and what they eventually become. Those are questions scientists are still wrestling with. And the deeper you go, the weirder it gets. Time slows down, space stretches, matter is torn apart at the atomic level, and the laws of physics themselves start arguing with each other. So today, we're taking a journey from the outside of a black hole all the way in, down past the event horizon, and as close as science currently allows us to go to the singularity. Let's begin. How a black hole is born. A black hole begins its life in a violent, catastrophic ending: the death of a massive star. When a star with more than around 20 times the mass of the Sun runs out of fuel, its core collapses under its own weight. Gravity wins. The collapse happens in less than a second, and the outer layers rebound outward in a supernova explosion, brighter than entire galaxies. But the core? It keeps collapsing. Atoms collapse. Electrons and protons merge into neutrons. Then even neutrons can no longer resist gravity. And at that point, there is no known force in the universe strong enough to stop the collapse. Gravity compresses everything into a single point of almost infinite density. Or at least, that's what classical physics predicts. This point sits at the center of what we call a black hole. But that's just the beginning of the story. The invisible sphere, the event horizon. To understand black holes, the most important idea is the event horizon. This is the boundary surrounding the black hole, the point of no return. Once anything crosses this boundary, it can't escape. Not because it's trapped in a physical shell, but because inside this boundary, escaping would require faster than light movement, and nothing with mass can do that. For a black hole with the mass of the Sun, the event horizon is only about 3 kilometers wide. For the supermassive black hole at the center of the Milky Way, Sagittarius A, the event horizon is roughly the size of Mercury's orbit. From the outside, the event horizon looks perfectly black. But just around it, things start to get messy. This is where one of the strangest predictions of Einstein's theory kicks in. Time slows down. Time behaves strangely near a black hole. If you hovered in a spacecraft safely outside a black hole's event horizon, something bizarre would happen. Time would pass more slowly for you compared to someone far away. This isn't sci-fi. Clocks run slower near massive objects. We've confirmed this using satellites and atomic clocks here on Earth. But near a black hole, the effect becomes extreme. If you watched a friend fall toward a black hole, they would appear to slow down, moving more sluggishly as they approached the event horizon. Their voice would deepen and stretch out. Their movements would freeze. And at the edge of the event horizon, they would appear to stop entirely. Forever. From your perspective, they never cross the horizon. But from their perspective, the fall takes seconds. Both views are correct. This is relativity in action. The fall. What actually happens to matter? Now imagine you're the one falling in. The moment you get close, the gravitational force on your feet is stronger than the force on your head. As the difference grows larger, the effect becomes lethal. The black hole stretches you violently in one direction and compresses you in another. Scientists call this spaghettification. For small black holes, like those formed from stars, this effect occurs outside the event horizon. For supermassive black holes, the stretching is gentle until after you cross the horizon. You wouldn't feel anything at first. But either way, you're being pulled into one place, the singularity. What is a singularity? The singularity is the core of the black hole, the place where Einstein's equations predict infinite density, infinite curvature of space-time, and zero volume. Physics breaks here, not metaphorically, mathematically. A singularity is simply a placeholder for our current theories can't describe what happens here. Quantum mechanics disagrees with Einstein's predictions. Einstein disagrees with quantum mechanics. And inside a black hole, they're forced to compete. Many scientists believe that the singularity is not a true physical point, but a region where a theory of quantum gravity, something we don't yet have, would take over. Some think matter might be compressed into the smallest possible volume, a Planck core. Others propose a ring-shaped singularity for rotating black holes. Some theories even suggest the core could be a bridge to another region of space-time, a wormhole. Though that's speculative. For now, the singularity remains the most mysterious object in physics. Do black holes live forever? For decades, we thought black holes were eternal. But in 1974, Stephen Hawking made a groundbreaking discovery. Black holes evaporate. They emit radiation due to quantum effects near the event horizon, something now called Hawking radiation. Over extreme timescales, black holes shrink and eventually disappear in a final flash of energy. A black hole the mass of the Sun would take 10 to the 67 years to evaporate. Supermassive black holes? Far longer. The universe itself may not last that long, but in the far future, long after the last stars have burned out, black holes will be the final objects to die. What we still don't know. Despite decades of research, black holes still hold many unanswered questions. We don't fully know what happens at the singularity. We don't know how information escapes or survives inside a black hole. The information paradox remains unresolved. We don't know how to reconcile general relativity with quantum mechanics in extreme conditions. But the most fascinating part is this. Black holes aren't just destructive. They help galaxies form. They shape cosmic evolution. And without them, the universe we live in wouldn't look anything like it does today. Black holes may be the engines of structure in the cosmos. Thanks for joining me on this deep dive into one of the strangest and most powerful objects in the universe. If you enjoyed this and want more space, deep dives, mysteries, and daily insights, make sure to subscribe for your daily dose of space.